Great friends. Hello, great friends. I hope you are having a very beautiful morning wherever you are, or good afternoon, good evening. Um, IBM is here to give you another episode of Learning Physics. Um, this is 2023, and I'm saying Happy New Year once again. If you're watching this video for the first time, do not forget to subscribe, download the document for the past paper questions that we are going to be using. This is Physics AS. This is going to be specifically paper 2, and these are solved past paper questions for AS Physics. Don't forget this is Physics 9702, that is Cambridge. So if you're not studying Cambridge, then this may not be of help. But of course, since there is overlap between there's overlap with all the curriculum. As long as it's physics, most of the concepts are going to remain the same. So do not forget that throughout these lessons, throughout these videos of waves, we are discussing questions involving longitudinal and transverse waves, Doppler effect, electromagnetic waves, superposition and stationary waves, diffraction, grating, and a lot many more, including progressive waves. So do not forget to download the document that you will need for the past paper questions. In case you have not yet downloaded the document, just simply pause the video, go to the video description, copy the link in the video description, paste it in your browser, and the document opens automatically for download. Download the document, print. You can print per topic and then use it for answering these past paper questions and for practice as you prepare for your exams. Without wasting any time, let me take you to the document of past paper questions so that we pick up from where we stopped in part 3. So in part 3, I guess we stopped on this question. We stopped on page, I think, 482, and we had answered this question here of stationary waves formed in pipes. So I want us to move straight away to the next question. I'll reduce the thickness of my pen. An arrangement that is used to demonstrate interference with waves on the surface of water is shown in the diagram here. So you can see the arrangement. We have a motor here. Of course, it is going to cause vibrations of the dippers D1 and D2. And the waves can travel from D1 to point A, D2 to point A, D1 to point B, D2 to point B, and so on and so forth. So two dippers, D1 and D2, are connected to a motor and a DC power supply. Initially, only D1 vibrates on the water surface to produce waves. Only D1 vibrates initially. The variation with the distance x from D1 of the displacement y of the water at one instant of time is shown in the figure. So this is what we have. Of course, before we go to the questions, it is the displacement against the distance. So it means we can find the amplitude and the wavelength. So amplitude, the scale here is 2 divided by 5. There are 5 small squares, 1, 2, 3, 4, 5. So the scale is 0.4. So this is 2.4, 2.8, and this is 3.2. Then the wavelength, if we start from this point here up to this point, you see that the wavelength is going to be 20. Okay, let's see the questions. Use the figure to determine the amplitude. That is the maximum displacement. We have already seen that is 3.2, and this is in millimeters. The question is wants answers in millimeters, so this is still 3.2. Then the wavelength of the wave. Determine the wavelength of the wave. The wavelength is the length for one complete cycle, or the distance between two successive crests or successive troughs. And this is actually 20 millimeters. So the wavelength is 20 millimeters. The two dippers D1 and D2 are made to vibrate and the waves are produced by both dippers on the water surface. State and explain whether these waves are stationary or progressive. The two dippers D1 and D2 are made to vibrate and the waves are produced by both dippers on the water surface. Of course, the waves are going to propagate through the water, so they are going to transfer energy from D1 and D2 to A or B. So that means these are progressive waves because energy is going to be transferred or moved through the water outwards from the dipper. So it is progressive. So we can simply say energy is transferred. Energy is transferred. Energy is transferred through the water outwards from the dippers. So progressive because it is a progressive wave where energy is transferred. Explain why D1 and D2 are connected to the same motor. Same motor, now this is now the concept of coherence. It is easier to produce coherent waves if the source is the same. So D1 and D2 are connected to the same motor so that the waves produced are coherent or maintain a constant phase difference. So to produce waves with a constant phase difference, produce waves with constant phase difference or to produce coherent waves. So that is why we are connecting to the same motor. The same motor, because the frequency of the waves depends on the source. So if the two dippers are connected to the same motor, that means the vibrations of these two sources will be in phase or will maintain a constant phase difference throughout, so the waves will be coherent. The points A and B on the figure 7.1 at distances from D1 and D2 as shown. So D1A is 5 centimeters. Where is the diagram? D1A, so this is 5.0 centimeters. And D2A is 7, D1B is 5, D2B is 6. So I'll just write these ones here. So D2A is 7 centimeters, D1B is 5 centimeters, and D2B is 6 centimeters. Okay. So we shall be able to get the path differences, I guess. State and explain the variation with the time of the displacement of the water on the surface at A. So at A, we consider D1A and D2A because we find the path difference at A. So the path difference therefore A is going to be 7 minus 5, which is 2 centimeters. That is the path difference. But what was the wavelength? Of course, 2 centimeters is to the same as 2 millimeters. 20 millimeters. That is the path difference. So path difference is 20 millimeters, but we had obtained the wavelength. The wavelength was 20. So you see the path difference is the same as one wavelength. That is constructive interference. When path difference is equal to n times lambda, and n is a whole number, then that means that is constructive interference. Alternatively, you can divide path difference, which is 20, by the wavelength, which is also 20, of course. So you see that path difference is equal to 1 wavelength, and that is constructive interference. So here you don't guess, you have the basics at the back of your mind. So we simply say the path difference is lambda, path difference is wavelength. Path difference is wavelength. Path difference is wavelength. So water vibrates or oscillates with an amplitude. Water vibrates or oscillates with an amplitude of about with an amplitude of about. What is the amplitude? We had already seen earlier on that the amplitude was of one wave of waves from D1 was 3.2. Now if the waves from D2 also have amplitude 3.2 and constructive interference occurs, so the total displacement will be 3.2 plus 3.2, which is equal to 6.4. So the waves, the water vibrates or oscillates with an amplitude of about 2 times 3.2, which is equal to 6.4 in millimeters. Since constructive interference occurs, so somebody may be wondering, why did we say 2 times 3.2? Now, initially when we had D1 alone, the amplitude was 3.2, but remember these were coherent sources, so the waves emitted were actually going to be identical. So since the waves were identical, it means the amplitude of the waves from D2 were also 3.2. And when they combine for constructive interference, the total amplitude is going to be 3.2 plus 3.2, which is approximately 6.4 millimeters. Then at B, let's check the path difference for B. So for B, path difference is 6 minus 5, which is 1 centimeter. That means path difference is 1 centimeter is 10 millimeters. So that means if I divide path difference by the wavelength, path difference over wavelength is going to be 10 over 20. So you notice that path difference is equal to a half wavelength, or lambda over 2. That is destructive interference automatically. So in B, path difference is okay, let me just write it here, is 6 minus 5, which is equal to 1 centimeter, which is equal to 10 millimeters. Path difference is equal to that, and 10 millimeters is the same as wavelength over 2. That is equal to wavelength over 2, so destructive interference occurs. I know some students said I don't write very well, so I need to try and improve. So destructive interference occurs. So there will be little or no amplitude. or there will be little or no displacement at all. So because the path difference is equal to lambda over 2, then we expect destructive interference. Remember, that means the phase difference is 180 degrees. It means a crest from say D1 is meeting with a trough from D2. Cancellation occurs, destructive interference. A progressive wave transfers energy. A stationary wave does not transfer energy. State two other differences between progressive waves and stationary waves. Okay, so to begin with, a progressive wave, we have already seen that for progressive waves, all particles will reach the same maximum displacement. In other words, all particles have the same amplitude, unlike a stationary wave. So one, for progressive wave, all particles have the same amplitude. In other words, they reach the same maximum displacement. Unlike stationary. That's number one. So unlike stationary waves, for progressive waves, all particles will always reach the same highest point. Number two, you can talk about stationary. I'm giving as many as I can. Stationary, oh, by the way, this is the same as this. You could say progressive, all particles have the same amplitude. Unlike stationary, or you say for stationary, as for stationary, we don't expect an amplitude, no amplitude at nodes, and maximum amplitude and at the antinodes. No amplitude at the nodes and maximum amplitude at antinodes. So that is this you either mention this or this, not the, because this is, it means the same. When I say for progressive, all particles have the same amplitude, unlike stationary, it is similar to saying for stationary, no amplitude at the nodes, but there is maximum amplitude at the antinodes. Number two, a progressive, we know that adjacent particles will never be in phase, but for stationary, two neighboring particles are in phase. So for progressive, adjacent particles are not in phase. Adjacent particles are not in phase. For stationary, wave particles are in phase between adjacent nodes. So for a stationary wave, if this is one of the segments, remember, this is another segment, this is a node, and there's a node here. all particles in between the two nodes vibrate in phase. However, remember we said particles between two adjacent antinodes are 180 degrees out of phase. Those between two nodes are in phase. Those between two antinodes are going to be 180 degrees out of phase, because all particles in one segment vibrate in phase with each other. That's why I said for stationary wave, particles are in phase between adjacent nodes. That is another difference. Okay, a stationary wave is formed on a stretched string between two fixed points A and B. The variation of the displacement y, remember it is a stationary wave. The variation of the displacement y of particles on the string with distance x along the string for the wave at time t equals to 0 is shown here. So at t equals to 0, we have a horizontal line, that is destructive interference. We have destructive interference. At t equals to 0, we have a horizontal line, that is destructive interference. The wave has a period of 20 milliseconds and a wavelength of 1.2 meters. The maximum amplitude of the particles of the string is 5 millimeters. That is obviously meaning that when I sketch a graph, it will not go beyond 5 millimeters, because that is the maximum. It will not go beyond 5 millimeters. So my graph will not go beyond this. So the maximum amplitude of the particles on the string is 5 millimeters. On the figure, draw a line to represent the position of the string at t equals to 5 milliseconds. At t equals to 5 milliseconds. Remember, the wave has a period of 20 milliseconds. What is 5 milliseconds? I think 5 milliseconds is a quarter of a cycle. That is 20 divided by 5. That is a quarter. That is, yes, 5 milliseconds is a quarter of a cycle. That is 5 over 20. Because one cycle is 20 milliseconds. So 5 over 20, that is a quarter of a cycle. A quarter cycle. So what happens at if at t equals to 0, we are starting with a destructive interference, or that is 0 amplitude. Then at a quarter a cycle, what has happened? A quarter a cycle means that at a quarter a cycle, because if at t equals to 0, we are starting with a horizontal line. Then that means after a quarter a cycle, because another complete cycle will come in after 20 milliseconds. So it means at a quarter a cycle, we should be having maximum displacement. But since the wavelength is 1.2, then how many cycles can I fit in this on this grid? So 1.2, these are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. So 1 divided by 20, each small square is 0.05. Now I want 1.2. So this is 1.1. I think 1.2 is there. That is one cycle. One cycle is here. Then the second cycle is going to be 2.4. So 2.1, 2.2, 2.3. I think the second cycle will be there. A half a cycle is 0.6. 0.6, I will divide this by 2. 0.6, this is 1, 2, 3, 4, 5, 6. I think 0.6 is here. That is 0.6, which is half a cycle. And a quarter cycle, it will be 0.3. 1, 2, 3. That is 0.3. This is, remember, 1.2. Then This is 1, 2, 3, 4, 5, 6. This will be 1, I think this will be 1.8. And somewhere here, 1, 2, 3, this will be somewhere here. Then 1, 2, 3, that is in the middle somewhere there. Okay. So after 5 milliseconds, if at equals to 0, we have a horizontal line. Then it means after 5 milliseconds, that is a quarter a cycle, we shall have maximum displacement. Therefore, we shall have maximum displacement at a quarter cycle. So this is going to be maximum displacement. The graph will go to maximum displacement there. Of course, at half a cycle, it comes back to 0. Then it goes to 1, 1, 2, 3. I think it will be going to maximum displacement here. And it comes back to 0 at 1.2. That is one cycle. Then 1, 2, 3. It is maximum again here. Then it comes at 1.8. It comes back to 0. Then again maximum at this point. And again it goes back to 0. Hope I've sketched it correctly. Let me check. 1, 2, 3. 1, 2, 1, 2, 3. 1, 2, 3. Okay, it passes around here. I'm simply trying because I know after every 6 boxes there should be some guidance for the graph. 1, 2, 3 we reach maximum. 1, 2, 3 we reach 0. 1, 2, 3 maximum. So it is maximum here. 1, 2, 3 we reach 0. 1, 2, 3 we reach maximum. 1, 2, 3 we reach 0 here. I think this is where we have 1.8. So the graph goes back to 0 around here. It's hard to sketch with a what on a computer, but 1, 2, 3. So it is here. It's around here. So it reaches maximum around there. Then it goes back to 0. So that is the graph. Number 1, of course, we have 0 displacement at, you expect y to be 0 at x equals to 0, x equals to 0.6, x equals to 1.2, x equals to 1.8, and x equals 2.4. So you can check from the graph. Wherever the graph is crossing the x-axis, it is at those values of x. And of course, we know that the peaks are going to be at 0.3, like here. And 1.5. I think this is 1.5. Yes, this is 1.5. Then the troughs are going to be at, this is 0.9, and this is going to be 2.1 meters. So you can check when you are plotting, you check that your troughs are those points. That is after 5 milliseconds. State the phase difference between the particles of the string at x equals 0.4 and x equals to 0.8. 0.4, I think 0.4 is somewhere here. Remember, whenever the displacement is 0, we have a node. So x equals 0.4 should be around here in this region here, and x equals 0.8 is going to be in this region here. And you will notice that I said when the displacement goes to 0, it means there is a node. So if there is a node here, and there is a node here, there is a node here, it means this is a different segment, the other one is also a different segment. And that means it's like we have three nodes we are comparing here. We have a node here, we have a node there, and a node here. So 0.4 is in this part here, and 0.8 is in this part here, because remember, we have 1.2 somewhere here. And this was 0.6, I guess, and this is 0. So we have a node, we have a particle at 0.4 is in this segment, a particle at 0.8 is in the other segment. So they are in two neighboring segments, so they are 180 degrees out of phase. So the phase difference there is 180 degrees. Remember, it is a stationary wave, not a progressive wave. So 180, I can write degrees. Oh, I know 180 is pi, so I can write pi, and the unit for pi will be radians. State and explain the change in the kinetic energy of a particle. State and explain the kinetic energy of a particle. State and explain the change in kinetic energy of a particle at an antinode between t equals to 0 to t equals to 5 milliseconds. A numerical value is not required. I want you to recall that we have seen that for t equals to 5, for t equals to 5.0 milliseconds, this was a quarter of a cycle. And here particles reached maximum. Particles reach maximum displacement. And remember, at maximum displacement, velocity is 0. What does that mean? At maximum displacement, velocity is 0, which means at maximum displacement, there is no kinetic energy. The particles will momentarily go to rest. But then, at t equals to 0, the particles, you can even see from the graph that at t equals to 0, the displacement is just starting to increase. That means the particles are having a kinetic energy. So that means the kinetic energy is going to be decreasing because at maximum displacement it becomes 0. So it means the kinetic energy decreases from 0 at t equals to, decreases from a certain value at t equals to 0, and it reaches 0 at t equals to 5, because at t equals to 5 the particle reaches the maximum displacement where velocity becomes 0. So we say at t equals to 0, the particle has kinetic energy. At t equals to 0, the particle has kinetic energy as it is moving. And at t equals to 5 milliseconds, there is no kinetic energy. Why is there kinetic energy? Why is there no kinetic energy? As the particle is stationary. As the particle is stationary. Why do we say that the particle is stationary? It has reached maximum displacement. it has reached maximum displacement. So in conclusion, we are saying kinetic energy decreases. So kinetic energy decreases, and it decreases between t equals to 0 and t equals to 5 milliseconds. So the kinetic energy is decreasing from at t equals to 0. We see that at t equals to 0, the particles were passing equilibrium, so they had zero displacement, they were passing equilibrium, so they had kinetic energy actually. And then at t equals to a quarter a cycle, the particles had reached maximum displacement, and therefore the kinetic energy becomes zero because the speed at maximum displacement is zero. Okay. Two overlapping waves of the same type travel in the same direction. The variation with the distance x of the displacement y of each wave is shown in the figure here. So they've showed us that figure. You can have a look at it. So the speed of the wave is 240 meters per second. The waves are coherent and produce an interference pattern. Coherent meaning they maintain a constant phase difference. Explain what is meant by, explain the meaning of coherence and interference. Of course, coherence is maintaining a constant phase difference. Maintaining a constant phase difference between two waves. That is coherence, maintaining a constant phase difference between two waves, and of course of interference, that is overlapping of two waves. There could be more than two, but I'll just consider overlapping of two waves resulting into, of course, when overlapping occurs, this results into addition of displacement, resulting into addition of displacements of the waves, or resulting into combination of these displacements of the waves. Overlapping of two waves resulting into addition of displacements. That is the algebraic sum. Addition of displacements of the waves. So use a figure to determine the frequency of the waves. So we can, of course, we know frequency is equal to V over lambda using the general wave equation. And V is given as 240 meters per second. All we need is the wavelength. So from the graph, let's check the wavelength. So if I use the simplest one to use, I think is going to be on the x-axis, each small square is 0.5 divided by 10, which is 0.05. So I'll use a simpler wave, which is the one at the bottom, I think, which stops up to here. That is one cycle. So if if this is 3, this is 3.1, that is 3.2. So because one small square is 0.05, so that is two small squares will give 0.1. So that means the wavelength is 3.2. So I'll say divide by 3.2. And we want the answer in hertz, so I just divide 240 by 3.2, that is 75. So the answer here is 75 hertz. State the phase difference between the waves. Phase difference between the waves. We need the distance. Since it is displacement against the distance, we shall need the distance out of step, which can be this distance here. This is 0.5, 0.6, 0.7, 0.8. That is 0.8. And then here it is 1.5, 1.6. So 1.6 minus 0.8, that is 0.8. So the distance out of step is 0.8. So the phase difference, which I'm calling phase, is going to be 360 into the distance out of step over the wavelength. So this is 360 into distance out of step. We have seen it is 0.8 and the wavelength was 3.2. 0.8 divided by 3.2 times 360, that is 90 degrees. So the phase difference is 90 degrees. 90 degrees, or it is pi over 2 in radians. But the question wanted the answer in degrees. Use the principle of superposition to sketch on the figure 6.1 the resultant wave. We are going to use the principle of superposition, which states that the algebraic sum, actually when two waves overlap, total displacement or the total displacement or resultant displacement is the algebraic sum of the individual displacements. So we are just going to sum up the displacements. If for the first wave the displacement is 0, for the second wave the displacement is 2, the sum is 2. So the graph starts from there. At the point where they meet, I think this is 1.5. They are meeting at 1.5. So the other one brings 1.5 plus 1.5, the total becomes 3.0. So at the point where the waves meet, we shall go up to 3.0, so that will be the point. Then when the other wave goes to 0 at around this point, the other one is at 2. So the sum is 2.0. So this is going to be the point. We have added 0 plus 2. Then we go to the bottom. So this is when this is at 0, at 1.6 it is at 0, and the other one is at -2. So 0 plus -2 is -2. So the point is here. Again, they meet at -1.5. -1.5 plus -1.5, that gives us -3. So where they meet, the graph goes back to -3. Again, when the other one goes to 0, the other one is at -2, so the sum is -2. 0, -2, the sum is -2, that is the point. Again, one is at 0, the other one is at +2. 0, +2, the sum is +2, so that is the point. Then again they meet at 1.5, 1.5 plus 1.5, that is 3. So where they meet, it goes to 3. And finally, 0 plus 2, it is 2, so that is the point. So I'll increase the thickness Let me even change the color for easy clarification. So our graph would look like this. Yeah, so you can draw a better one, but it should be a smooth graph, a smooth curve, as long as it goes through those exact points, because the algebraic sum is what we are interested in here. So this will be our new graph, and we have used the principle of conservation of momentum. I mean the principle of superposition, not conservation of momentum. Okay, so your graph should look like that. Remember how we obtained it by just adding the displacements at every point, every convenient point. Okay, so here we have a laser, and we have a double slit as shown here. Laser light of wavelength lambda of 546 nanometers is incident on the slits S1 and S2. The slits are at a distance 0.13 millimeters apart. That is, since this is a double slit, that is going to be A. The distance between the slits and the screen is 85 centimeters, so this is D. 2 points on the screen are labeled A and B. The path difference between S1A and S2A is 0. So that means this is going to be the zero order maxima. The central order maximum. The path difference between S1B and S2B is 2.5. That is 5/2 lambda. That is, of course, destructive interference. That is a minima. It is a darker fringe. So here we have a dark fringe. Maxima and minima of intensity of light are produced on the screen. Calculate the distance AB. So we are going to calculate the distance AB. So first of all, remember that lambda is equal to AX divided by D, where X is the distance between two successive darker fringes or two successive bright fringes. So X is going to be equal to lambda times D divided by A, and X is going to be wavelength, which is 546 times 10 power negative 9, then times D. D is 85 times 10 power negative 2 divided by A. A is the slit separation, which is 0.13 times 10 power negative 3. So we are finding X. Remember, X is specifically distance between two successive bright fringes or two successive darker fringes. So X is going to be equal to, so from my calculator, I'm getting X as 3.57 times 10 power negative 3 meters. So we want to find distance AB. Now for a layman, I'll do this for a layman, but for experts, I know that they will be able to see that distance AB is equal to 2.5 times 3.57 times 10 power negative 3, which from my calculator would be equal to 2.5 times 3.57, and that is 8.93 times 10 power negative 3. For a layman, I want to show them this. I want to show you this. I will just draw a larger screen so that I show you. Number one, this is where there is A. At point A, we have a bright fringe. That is bright. A bright fringe is followed by the first darker fringe, then followed by the first bright fringe. This is the zero order at A. This is zero order at A. So this is the first darker fringe, where here the wavelength is going to be lambda over 2, the path difference. Then the first bright fringe, the wavelength, the path difference is lambda. Then the second darker fringe, where the wavelength is 3 lambda over 2, the path difference is 3 lambda over 2. Then we have a bright fringe. Then again we have a darker fringe where the path difference is 5 lambda over 2, and 5 lambda over 2 is 2.5 lambda. So that is darker fringe. So you can notice that x is the distance between every bright fringe. So this is x, that is x, and you remain with the half of x. That is a half of x. So you have x plus a half of x, because the distance between a bright fringe and a darker fringe is a half of x. So that means you have 2.5x. That is the distance between A and B, because at A we had a zero order, and at B we had a darker fringe where the path difference was 2.5 lambda. Therefore, we can now agree that the distance between A and B is 2.5x. Okay. The laser is replaced by a laser emitting blue light. Initially, we had a laser producing wavelength 546 nanometers. And now we are replacing the laser with one that produces blue light. State and explain the change in the distance between the maxima observed on the screen. What do we know about blue light? When you look at the visible spectrum, ranging from 400 nanometers to 700 nanometers. Richard, actually this is violet, orange, red, orange. Richard of York gave birth in vain. So blue is somewhere here. And the average of all these, they've given us 546, and 546 is approximately here in the center. Around here, around the green yellow, this is where we have 546. It's around 550, which is the average of these colors around here. So it means the blue is at a shorter wavelength. So blue has a shorter wavelength than 546. And remember the expression, wavelength is directly proportional to x. Therefore, if the wavelength has reduced, it means x also decreases. So we simply say blue light has a shorter wavelength. Blue light has a shorter wavelength, and we know that wavelength is directly proportional to x from the expression above. So the distance decreases. So the distance decreases. A source S of microwaves is placed in front of a metal reflector R as shown in the figure. A microwave detector D is placed between R and S. Describe how stationary waves are formed between R and S. So how is the stationary wave formed? Of course, the source produces a wave which travels to the reflector, and the reflected wave meets with the incident. Of course, they are already of the same type since it is just the reflected and the incident meeting. They travel at the same speed, they have the same frequency, and when they overlap, a stationary wave is formed. So a microwave from S a microwave from S, that is from the source, is reflected at R, that is at the reflector. The reflected and further incident wave overlap. The reflected and further incident wave overlap, or they meet. They overlap or meet, and when because since the waves are of the same frequency, wavelength, speed, then a stationary wave is, or stationary waves are formed. Since the waves have the same frequency, or wavelength, and speed, then a stationary wave is formed. So a stationary wave is formed because I can't talk about moving in opposite directions because I mentioned reflected. So it means they're already moving, one is moving in the opposite direction to the other. Explain, describe how D is used to show that the stationary waves are formed between R and S. So how are we going to use the detector to show that there is a stationary wave formed between R and S? We have to move the detector between R and S, and we detect points of maxima, minima, maxima, and so on and so forth. If we can detect points of maxima, minima, maxima, minima, maxima, and so on and so forth, it means we are detecting points of nodes and antinodes. Nodes and antinodes are characteristics of stationary waves. Therefore, we have to move D. So D is moved. D is moved between R and S. And the points of maximum, minimum, points of maximum, minimum, maximum, and so on. Points of maximum, minimum, maximum, and so on are observed. On the meter or on the meter, because they have showed the meter here. Points of maxima, minima are observed on the meter. Of course, maxima, that is where there is maximum displacement, and minimum, zero displacement. On the meter, then we know that a stationary wave is formed. I say the maxima is antinode, minima is node, and nodes and antinodes show stationary waves. Again, describe how the wavelength of the microwaves may be determined using the apparatus in the figure. Remember, we know that the distance between an antinode and an antinode is half wavelength, or the distance between a node and a node is half wavelength. Suppose we measure distance between two successive minima or two successive maxima and divide it by 2, and multiply it by 2, then we get wavelength. So that is very simple. You can say measure the distance between adjacent minima, that is, of course, that is the nodes, or maxima, you measure distance between adjacent maxima. These are the antinodes. The wavelength is going to be twice. We multiply that distance by 2. So the wavelength is twice. So the wavelength is going to be twice distance between adjacent nodes, that is distance between two successive minimum, or distance between adjacent antinodes, that is two successive maxima or adjacent maxima. Okay, the wavelength of the microwaves in B is 2.8 centimeters. Wavelength is 2.8. Calculate the frequency in gigahertz. So we know that frequency is equal to V over lambda. These are microwaves. You don't need to ask for the speed of microwaves. That is 3.0 times 10 power 8 divided by the wavelength, which is 2.8 times 10 power negative 2, because it was in centimeters. So I press my calculator. From my calculator, this is 1.07 times 10 power 10 hertz. We want the answer in gigahertz. I said to bring a prefix, you divide by its value. So it is 1.07 times 10 power 10 divided by the value of giga, which is 10 power, giga is 10 power, I think it's 10 power 9. And this is giving me 11. Approximately 10.7, which is 11. That is 11. Light from a source S1 is incident on a diffraction grating as illustrated in the figure. So we have a zero order in that line. The light has a single frequency, that is, it's monochromatic. The diffraction grating has 650 lines per millimeter. That means per meter we shall multiply by 1000. Calculate the number of orders of diffraction of diffracted light produced by the grating do not include the zero order. So we want the number of orders without including the zero order. So if we want the number of orders, it means sine theta must be equal to 1. So remember, n lambda is equal to d sine theta for diffraction grating. And we don't have the wavelength, I think. We have the frequency, and it is light, we know the speed, so we can find wavelength. So wavelength is going to be v over f, which is 3 times 10 power 8 divided by f, which is 7.06 times 10 power 14. That is wavelength. We want the maximum value of n. And remember, sine theta is going to be equal to 1 for maximum value, and sine theta is going to be equal to 1. So it means that n is going to be equal to d over the wavelength. I'm just going to replace this. So n is going to be d. What is d? They gave us 6,650 lines per millimeter. 650 lines per millimeter. This is the same as 650 times 1,000 to have lines per meter. Because 1 millimeter is 1 meter is 1,000 millimeters. So we multiply by 1,000 to get the number of lines in 1 meter. And number of lines, how is number of lines related to d? So let me first come up with the number of lines here. We know that d is equal to 1 over n, or the other way around, number of lines is 1 over d. Okay, d is equal to 1 over n. So d will be equal to 1 over 650 times 1,000. That is d. Now I'm substituting this expression to get small n. Small n is d, which is 1 over 650 times 1,000. That is d. I'm substituting this expression. Then divide by, or times 1 over lambda, which is the reciprocal. So times 1 over lambda, which is the reciprocal, which would be 7.06 times 10 power 14 divided by 3 times 10 power 8. If you are poor at mathematics, you can just press calculators at every stage. For those good at mathematics, we press our calculator at once. So I have something like that. I just press my calculator at the end of it all to see what this value is. So from my calculator, I'm getting n as 3.6. Since we cannot have 0.6 orders, so we shall round off the smallest whole number, which is going to be 3 orders. We cannot round off to 4 orders. It means the other one cannot fit on the screen. So we just take the number which fits on the screen, which will be 3 orders. So the maximum is going to be 3. Since they did not tell us to include the 0 order, so it starts from n1, n equals 2, n equals 3. But there is no n equals to 0. And we did not include the orders below. We did not include the orders on the other side because they are always symmetrical around the 0 order. So the number is going to be 3. The second source S2 is used in place of S1. The light from S2 has a single frequency lower than that of the light from S1. State and explain whether more orders are seen with the light from S2. Remember, the number of orders is inversely proportional to wavelength. And remember, wavelength is inversely proportional to frequency. So frequency has been decreased. That means the wavelength has increased. When the wavelength has increased, it means the number of orders must decrease because they are inversely proportional. So lower frequency means greater wavelength. Lower frequency means greater wavelength. So fewer orders. So we expect fewer orders. Okay. A beam of vertically polarized monochromatic light is incident on a polarizing filter as shown in the figure. So here, this is Malus' law. If you have studied polarization, this is Malus' law. Vertically polarized light incident on the polarized incident light beam. We have a polarizer and the transmission axis is shown vertically. The transmission axis of the filter is initially vertical, and the transmitted light beam has the same intensity as the incident light beam. The transmitted has the same intensity as the incident because it's just going through because it is just vertical. The filter may be rotated about the direction of the light beam to change the angle of the transmission axis to the vertical. State one angle of the transmission axis to the vertical that results in no transmitted light beam. Remember, of course, we know that I equals to I naught cos squared theta. If theta is equal to 90 degrees, I is equal to 0. So the angle here is 90. If theta is 90 degrees, the transmitted intensity is 0. So the angle there is 90 degrees. Then the filter is now positioned with its transmission axis at an angle theta to the vertical as shown in the figure. So the axis has been rotated through an angle theta. The ratio intensity of transmitted light over intensity of incident light is equal to 0.75. Calculate the angle theta. So we know from Malus' law, the intensity transmitted is equal to I naught cos squared theta. So it means I over I naught is equal to cos squared theta, but they've told us I over I naught is 0.75. So this is 0.75. So it means cos theta is equal to the square root of 0.75. And what is theta? So theta is going to be the cos inverse of the square root of 0.75. Of course, the root of 0.75 from my calculator, cos inverse, that is 30 degrees. So theta is going to be 30 degrees. Then calculate the ratio amplitude of the transmitted light over amplitude of incident light. Since it is amplitude and intensity, we know that intensity is directly proportional to amplitude squared. Therefore, intensity is equal to a constant times amplitude squared. So let's say the transmitted light is A1, has amplitude A1, and the incident light has amplitude A0. So we are going to have two equations here. We shall say I1 is equal to K A1 squared. I will divide by I0. I will divide by K A0 squared. Those are two equations which I have divided. So K has cancelled out. And remember, I is the transmitted, I1 is the transmitted, I0 is the incident. And we have already seen that I over I0, maybe let me just use I and I0 for simplicity. Let the other one be I0 So this is I and the other one is I naught. So the other one will be A, the other one will be A naught. We already have that I over I naught is 0.75. So it means A squared over A naught squared is going to be 0.75. So what does that mean? A over A naught is going to be the square root of 0.75. What is that value? So from my calculator, the square root is 0.87 as the ratio A over A naught, amplitude transmitted over incident amplitude. By reference to the direction of transfer of energy, state what is meant by a longitudinal wave. That one is now a common question. A longitudinal wave, we know that particles vibrate perpendicular. So this is a wave in which particles vibrate, or longitudinal, that is parallel, not perpendicular. Particles vibrate parallel to the direction the particles vibrate parallel to the direction of transfer of energy. So that is a longitudinal wave. The particles vibrate parallel to the direction of propagation of energy. Particles vibrate parallel to the direction of transfer of energy. These particles. Okay. A vehicle travels at a constant speed around a wide circular track. It continuously sounds its horn, which emits a single note of frequency 1.2 kHz. An observer is a large distance away from the track, as shown in the view from above in the figure. Okay, so this is as shown from the view, a view from above. Figure 4.2 shows the variation of course, the track is moving like that, the vehicle is moving like that. Let's assume when it is here, it is moving in that direction, that is towards. When it is in this position, it is moving towards. Of course, when it is here, it is going to be moving downwards. And when it is here at the bottom, it is going to be moving in that direction. That is our way. So this is towards, and this is away. Okay. So figure 4 shows the variation with time of frequency f of the sound of the horn that is detected by the observer. The time taken for the vehicle to travel once around the track is t. So one cycle is t. So t, that is one complete cycle, is t. So this is the second cycle. Okay. Explain why the frequency of the sound detected by the observer is sometimes above and sometimes below 1.2. So you can even see from the graph it is sometimes above and sometimes below. So it means at some point it is above when it's moving towards, and it is going to be below when it's moving away from the observer. So the frequency increases above 1.2 as the vehicle moves towards the observer, and decreases below 1.2 as the vehicle moves away from the observer. So frequency increases above 1.2 kilohertz as the vehicle moves towards the observer and decreases below 1.2 kilohertz as the vehicle moves away. So that is Doppler effect anyway. State the name of the phenomenon. That is straight away, that is Doppler effect. On the figure 4.1, mark with the letter X the position of the vehicle when it emitted the sound that is detected at time t. That is after one period. We see after a time t, the frequency is above 1.2. It must be moving towards the observer. Where is it moving towards the observer? It is at the top. So this is where we mark X. They didn't tell us to draw the diagram of the vehicles here, so I just drew them here to show you. So it is moving towards the observer when it is at the top, because at the top the arrow points to the right. So X will be at the top. So X is going to be here. Then on the figure, mark with the letter Y the position of the vehicle when it emitted the sound that is detected at time 9t over 4. 9 quarters. 9t divided by 4. 9t divided by 4. 9 divided by 4 is what? 2.25t. So 2.5 a period will be, I think, somewhere here. This is 2.5 a period. This is 2.5, 2.5t. Again, divide this by 2. When I divide 0.5 by 2, I get 2.25. So 1, 2, 3, 4, 5. I think it is here. This is 9 over 40. 1, 2, 3, 4, 5. 9 over 40 must be around here. Nine over 40 is around here. And this is, I think it is along this point. 9 over 40 is giving us 1.2. And 1.2 is the normal frequency. So this is most likely going to be at this point here, because here it is going to be below. At this point is moving away, it is going to be below. So 1.2 must be here. It must be at this point here. So this is where I have my Y. So Y must be there. So it is quite technical. People would think they would think X would be here because it is closest to the observer. But remember, I have drawn a diagram of the vehicle and I said at this point here the arrow will be pointing downwards. It is not moving towards the observer. So at Y, it must be moving at the normal frequency, which is, the observer must be detecting at the normal frequency, which is 1.2, because the vehicle is not moving towards him or away from him. But at the bottom here, it is moving away. So here the frequency will go below 1.2. At the top here, the vehicle is moving towards. The frequency is going to be above 1.2. So X is at the top and Y is at this extreme end, that is to the extreme right. That's where we have our Y. So on your graph, on your diagram, I expect you to label y on the extreme right and to label x at the extreme top. The speed of the sound in the air is 320 meters per second. Use the figure to determine the speed of the vehicle in B. So the speed is 320. I'll use, let me use maybe maximum frequency, no problem. From the vehicle, the figure maximum frequency is 1.4. I'll use maximum frequency. That is frequency above when it is moving towards. So frequency, observed frequency is going to be V over V minus speed of the source divided by, times frequency of the source. If I use maximum frequency, the denominator shall have minus. So this will be 1.4 kilohertz, because the speed is 320 divided by 320 minus Vs. The normal frequency is 1.2 kilohertz. Kilo has cancelled, so I don't need to add it here. I know if I put kilo on the left and kilo on the right, they will cancel out. So what I want is to solve this equation. By cross multiplying, I have that 320 minus Vs is equal to 320 times 1.2 divided by 1.4. So I'll just press my calculator. 320 times 1.2 divided by 1.4. Then I subtract 320 minus the answer. That is 45.7. So Vs is equal to 45.7 meters per second. That is method 1. You could use also minimum frequency. If I use the minimum frequency, the formula slightly changes. I'll use F naught is equal to V over V plus Vs. This is times Fs. I'm using minimum frequency. The minimum frequency is below 1.2. And from the graph, the minimum frequency is here. And this is going to be, this is 1, I think this is 1.05, because the scale here is 0.2 divided by 10, 0.02. So this is in the center, 0.02, 0.04, 0.05. So that is 1.05. So I can use that. So 1.05 is the observed. Speed is 320 plus Vs. Normal frequency 1.2. The kilo are still cancelled out. So still, when you cross multiply, you have the 320 plus Vs is equal to 320 times 1.2 divided by 1.05. So still press your calculator, you will get 45.7. So this is approximately 46. Okay. A child sits on the ground next to a remote-controlled toy car. At time t equals to 0, the car begins to move in a straight line directly away from the child. The variation with the time t of the velocity of the car along the straight line is shown here. The car is moving. The car begins to move away from the child, and the velocity against time is shown here. The car's horn continuously emits sound of frequency 925 between t equals to 0 and t equals to 6. The speed of the sound in the air is 338 meters per second. The car's horn continuously emits sound of frequency 925 hertz. Between that, this is a repetition. Describe qualitatively. Qualitatively does not need quoting values. If any, in the frequency of the sound heard by the child that was emitted from the car horn from t equals to 0 to t equals to 2 seconds. So let's look at the graph. T equals to 0 to t equals to 2 seconds. Remember, it's moving away. If it's moving away, the formula we are considering, the vehicle is moving away, the formula we are considering is F naught equals to V over V plus Vs times Fs. Is moving away, that's why I have the plus here. But now let's look at the speed. If the speed is not changing, then there is no problem on the frequency. But if the speed is changing, if the speed of the source is changing, then there's a problem with the frequency. Between t equals to 0 to t equals to 2.0 from the graph, you see that the speed is increasing. So it means Vs is increasing. The speed of the source is increasing, making the denominator to be larger, which means the observed frequency becomes smaller. Even though it's moving away, there is a decrease in the observed frequency. So here, this is a decrease. The reason is very simple. Speed is decreasing from the graph. I mean, speed of the source is increasing. That is just a simple explanation, although it is not required here. Then from t equals to 4 seconds to t equals to 6, let's look at the graph. 4 seconds to 6, you see the speed is decreasing. Meaning, if I use the same equation here, the speed Vs is decreasing. When Vs decreases, it means the denominator is smaller. This fraction will be larger. F naught increases. So here it increases. Increases because speed of the source, Vs, is decreasing from the graph. I'm saying this part is not necessary, it is just for explanation to see how we conclude, how we come to that conclusion that is increasing or decreasing. Determine the frequency to 3 significant figures of the sound heard by the child that was emitted from the car at time t equals to 3 seconds. 3 seconds, speed is constant, so there's no problem with that. We just use the formula. Remember, it was moving away. So observed frequency is equal to V over V plus Vs, then times Fs. So we want to determine the frequency of the sound heard by the child, that is the observed frequency. So this is going to be equal to 338 was the speed of the sound over 338 plus. At 3 seconds, the speed is, I think that is 12. Because the scale here is 1, so that is 12 meters per second. So this is going to be plus 12, then multiplied by the normal frequency. The normal frequency was 925. Answer. So this is going to be 893 hertz. Time taken for the sound emitted at time t equals to 4 seconds to travel to the child. At time t equals to 4 seconds. Here, remember, a child sits on the ground next to a remote controlled toy. At time t equals 4 seconds, the toy is at a distance which is equal to the area under the graph away from the child. So the sound must travel through this distance here, which is represented by the area under the graph, to reach the child. At time t equals 4 seconds, the toy is at a distance which is equal to the area under the graph, represented by this part here. So the sound must travel this distance, represented by the area under that graph, to reach the child. So it means to find the time taken, so I will say at t equals to 4 seconds, the toy is at a distance represented by the area under the graph. At time t equals 4 seconds, the toy is at a distance represented by the area under the graph from the child. I'm just putting this for explanation. And this distance is equal to a half. I think it is a trapezium. Yes, it's a trapezium, so a half. Or you can divide it into a triangle, which is a half times 2 times the height, which is 12, plus a rectangle, which is going to be 4 minus 2, that is 2 times 12. So that is 2 times 12. So this is going to be a half times the base, which is 2 times 12, that is for the triangle part, plus 2 times 12, that is for the rectangular part. And I think that is 12 plus 24, that is 36. So the sound must travel a distance of 36 to reach the child. The time it will take, time is going to be distance over the speed. Therefore, the time is going to be distance, which is 36 meters, divided by the speed, which is 338. And that gives us 0.107, or approximately 0.11. A tube is initially fully submerged in water. The axis of the tube is kept vertical as the tube is slowly raised out of the water, as shown in the figure. A loudspeaker producing sound of frequency 530 Hz is positioned at the open top end of the tube as it is raised. The water surface inside the tube is always level with the water surface outside the tube. The speed of sound in air in the tube is 340 meters per second. Describe a simple way that a student without requiring any additional equipment can detect when a stationary wave is formed. That is very easy. When you raise the tube, you will note positions of the tube where a much louder sound can be heard. That means resonance has occurred, so a stationary wave is formed. So the simplest is to note a position of the tube where a much louder, that is very important, where a much louder sound can be heard. So I said when a much louder sound is heard, then that means resonance has occurred, a stationary wave has been formed. So as the tube is raised, there are positions where a much louder sound is heard. When a much louder sound is heard, just know that resonance has occurred, a stationary wave has been formed. Determine the height of the top end of the tube above the surface of the water when a stationary wave is first produced in the tube. So the tube is going to behave as if it is a closed pipe. And for closed pipe, the first resonance occurs when we have something similar to this. That is when we have a quarter, a cycle. So first of all, this distance here is going to be a quarter a wavelength. It is going to represent a quarter wavelength. So if we need to find the wavelength, so wavelength is going to be V over frequency. The speed was 340. Then the frequency is 530. So that is the wavelength. And remember, the first resonance occurs when the distance or the length of the pipe the length of that part where we have the sound is a quarter wavelength. So it means the distance is going to be equal to a quarter a wavelength, which will be a quarter times 340 over 530. So 340 divided by 4 times 530. That is 0.16. So this is 0.16 in meters. Determine the distance moved by the tube between the positions at which the first and second stationary waves are formed. I think that distance is very easy. The easiest method is just to consider the second. For the second stationary wave, we expect something like this. We expect something like that, and that distance is going to be 3 over 4 of wavelength. You notice it is a half plus a quarter. Half a cycle plus a quarter cycle, that is 3 over 4 wavelength. So determine the distance moved by the tube between the positions at which the first and the second stationary waves are formed. So we just get the difference between the two. And the difference between the two is, I think it is half wavelength. So for the second, the distance is going to be the difference between those two. So distance is going to be 3 over 4 wavelength for the second minus 1 over 4 wavelength for the first, which I think it is 2 wavelength over 4, which is wavelength over 2. And remember, we got our wavelength. What was the wavelength? The wavelength was 340 over that. So this distance is going to be 340 over 530 times 1 over 2, because wavelength is 340 over 530. So 340 divided by 2 times 530. And this is equal to 0.32. So this is 0.32. The distance actually is this one here, which is half a cycle. Because the other one is a quarter, the next one is 3 over 4 quarters. When you subtract, then that is half a cycle, which is 0.32 meters. Okay, I think that is all. For a progressive wave on a stretched string, state what is meant by amplitude. Progressive. So amplitude is the maximum displacement of a particle on that string or on that wave. Maximum displacement of a particle on the string or wave. Because here we are referring to a string, that's why I brought in a string, but I will just have said wave. Maximum displacement of a particle on the string or wave, that is amplitude. Light from a laser has a wavelength of 690 nanometers in a vacuum. It is light, remember, you don't need the speed of light. You know it. Calculate the period of the light wave. So I want period, so I know that V is equal to lambda F. And of course, we know that F is equal to 1 over T. So which means that V is going to be equal to lambda over T. We want T. This implies that T is going to be equal to lambda over V. So lambda is 690 times 10 power negative 9. V is 3 times 10 power 8. So press our calculator. So this is giving us 2.3 times 10 power negative 15. A two-source interference experiment uses the arrangement shown in the figure. So we have a slit separation, distance between the slits and the screen, light from a laser, wavelength lambda. Light from a laser is incident normal on a double slit. A screen is placed to the double slit, parallel to the double slit. Interference fringes are seen on the screen at distance d from the double slit. The separation of the centers of the slits is A. Light has wavelength lambda. The separation x of the centers of adjacent bright fringes is measured for the different values of d. So we first of all go back to the equation. Okay, this is what the question wants. The gradient of the graph is g. Determine an expression in terms of g and lambda for the separation A of the slits. So it is a diffraction grating. I mean double slit. So for a double slit, lambda is equal to ax over d. When I try to make x the subject, x is equal to lambda over a times d. If I compare with y equals to mx plus c, the general equation of a straight line, compare with y equals to mx plus c, you see that, remember, m is the gradient. So you see that the gradient equals to lambda over a. So gradient is equal to lambda over a. So we say that g equals to lambda over a because g is the gradient, which means that a is equal to lambda over g. So we want here lambda over g. The experiment is repeated with slits of separation twice a. The wavelength of the light is unchanged. So you see that slit separation is directly proportional to the inversely proportional to the gradient if wavelength is constant. So when the slit separation is doubled, it means the gradient must be halved. You are seeing that slit separation is inversely proportional to the gradient. The slit separation has been doubled, so the gradient must be halved. A is doubled, G must be halved. Sketch a graph to show the results of this experiment. So we are going to halve this gradient. And halving this gradient is very easy. I will just divide the y values by 2. And since the first is represented by 5 small squares, I will divide it by 2. I mean 10 small squares, I will divide by 2 and there will be 5. 1, 2, 3, 4, 5. So my new line will just be here. Of half the gradient, it will be just here. I just divide the y values into 2. So the new graph will be just there. Maybe I can increase the thickness. Okay, so that is the new graph, half of the gradient of the original graph. State the conditions required for the formation of a stationary wave. I think those conditions are now obvious. We must have two waves or more waves, same type, same frequency, same wavelength, traveling, having the same speed, traveling in opposite directions, and they must overlap. So two waves two waves of the same type same frequency, same wavelength, two waves, same type, same frequency, same wavelength, traveling at the same speed. Traveling at the same speed in opposite directions. Overlap. They must be meeting, they must overlap to form a stationary wave. So they should be of the same type. That is very important. They should be of the same speed, they should be in opposite directions, and they should be meeting to form a stationary wave. State the phase difference between any two vibrating particles in a stationary wave between two adjacent nodes. So you have two adjacent nodes. You have a node somewhere here and a node somewhere here. We said all particles between two adjacent nodes vibrate in phase. So the phase difference is 0. All particles between two adjacent nodes vibrate in phase for a stationary wave. However, a particle between an antnode and another antnode, particles between two antnodes may vibrate 180 degrees out of phase. But between two nodes, they are in phase. Particles in the same segment, they are in phase, so the phase difference is 0. Okay. A motorcycle is traveling at 13 meters per second along straight road. The rider of the motorcycle sees a pedestrian standing in the road directly ahead. That means the motorcycle is moving towards, and operates a horn to emit a warning sound. The pedestrian hears the warning sound from the horn at a frequency of 543 hertz. The speed of the sound in the air is 334 meters per second. Calculate the frequency to three significant figures. Did I maintain three significant figures here? There was somewhere I saw three significant figures. I hope I've maintained them, because it is very important to maintain the same degree, the required degree of accuracy. Calculate to three significant figures of the sound emitted by the horn frequency. So because it is moving directly towards, the observed frequency is going to be V over V minus Vs. Because it is towards, it is minus times Fs. So the observed frequency is 543 because it is towards. Speed of sound is 334 over 334 minus the speed of the source is 13 times the normal frequency Fs. So just solve this by cross multiplying. So Fs is going to be 543 times 334 minus 13 divided by 334. 543 times 334 minus 13 divided by 334. That is 512.21. So F of the source is 521.9, or approximately 522, or 500, but they said to three significant figures, so it is 522. The motorcycle rider passes the stationary pedestrian and then moves directly away, so the frequency must be decreasing. As the rider moves away, he operates the horn for a second time. The pedestrian now hears sound that is increasing in frequency. Instead, it is supposed to be decreasing, but is now increasing. Because it's moving away, the observed frequency is supposed to be V over V plus Vs times Fs. Where here, if the speed is constant, then it means the frequency must be decreasing. But we are saying that the frequency is increasing yet is moving away. That means something must be happening to this Vs, so this Vs must be decreasing. State the variation, if any, in the speed of the motorcycle when the rider operates the horn for the second time. Because the pedestrian now hears a sound that is of increasing frequency, it is because the denominator is becoming smaller. The only way the denominator is becoming smaller is because Vs is decreasing. So we can say the speed is decreasing. A beam of vertically polarized monochromatic light is incident normally on a polarizing filter as shown here. The filter is positioned with its transmission axis at an angle of 20 degrees to the vertical. The incident light has intensity I0 and the transmitted light has intensity IT. By considering the ratio IT over I0, calculate the ratio amplitude of transmitted light over amplitude of incident light. Show you're working. I think that is an easy question. We know that intensity is directly proportional to amplitude squared. And we also know from Malus's law that intensity transmitted is equal to incident intensity I0 cos squared theta. So we're going to combine those two equations. So for the first one, intensity transmitted is going to be equal to K times the amplitude of the transmitted wave squared. I'm dividing by the incident intensity over K times the incident amplitude. That is 1. And also using Malus's law, intensity transmitted divided by I0 is going to be equal to cos squared theta. So it is going to be cos squared of 20. So I'm combining the two equations. So I'll simply say that because here K has cancelled, I'll simply say that A transmitted over A incident squared is going to be equal to cos squared of 20. The square is cancelled out because it is on both sides. So we say that A transmitted over incident value of A is simply going to be cos of 20. And cos of 20 is 0.94. So this is 0.94. Okay. The filter is now rotated about the direction of the light beam from its starting position, shown in the figure 5.1. The direction of rotation is such that the angle of the transmission axis to the vertical initially increases. Calculate the minimum angle through which the filter must be rotated so that the intensity of the transmitted light returns to the value that it had when the filter was at its starting position. So remember we started the transmitted intensity I transmitted is equal to I0 cos squared of theta. First of all, we got an intensity when theta intensity transmitted was IT when theta was 20, and we want to return to the same. So I will use simple mathematical principles. I think mathematical principles will be the simplest. For example, I will use the quadrants. So we had 20 degrees in the first quadrant. Remember, this is squared, so even if this is squared, that is intensity transmitted is equal to I naught cos theta, but is always squared. So it means we don't mind about the negative because it is always squared. So the next time we shall have, I think this is the first quadrant, all positive. The second one, cos is positive. All students take chemistry. All students take chemistry. All positive, sine is positive here. The rest are negative, but remember it is squared. So if it is squared, so here I will have 180 in this quadrant. I will have 180 minus 20, which is going to be 160. So that is 160. And therefore we have moved from 20 to 160. Remember here sine is positive and cos is negative, but remember it is squared. So this is going to be 180 minus 120, which is 160. So we have moved from 20, the change is from 20 to 160. So the change in the angle is from 20 degrees. No, the change is from 160 degrees. So I will say the change is 160 degrees minus 20 degrees, because we moved from 20 degrees in the first quadrant to 160 degrees in the second quadrant, because this is 20, so it is 160 degrees. Therefore, the change is from 20 degrees to 160 degrees, and this gives us 140 degrees. Since they wanted us to find the minimum angle through which the filter must be rotated, so it must be rotated from 20 degrees to 160 degrees. That means it is changing from 20 to 160. The change there is 140. So the answer here is 140 degrees. So that is, I use the simple mathematical principles. However, I would have used the graph of the trigonometry approach, but that would be a longer process. I would have used the trigonometric approach. Let me check. Cos of 120 squared. Yeah, cos of 160 squared is the same as cos of 20, but we have moved from 20 degrees to 160 degrees. So the change in the angle is 140 degrees. We have rotated through 140 further degrees. Okay, as we wind up, I think we can stop with this question. Yeah, we shall start from this point. So this is the end of part 4, and see you in part 5. We shall start from here in part 5. Stay blessed. Bye bye.